Hey, how you guys doing? So I just wanted to go over a quick question that I was given by my professor, Professor Chan. This is a quiz that he gave us, and this is the circuit that we're supposed to analyze. And the first part of this quiz is to solve this circuit for Vs, this voltage right here, using nodal analysis. And I'm going to go ahead and redraw the circuit so that it'll look a lot easier and it'll look a lot more cleaner for me to do the nodal analysis, and then I'll continue with the rest of the problem. Hey, so here's the circuit redrawn, and if you don't understand how we redrew this, I'll explain it. So actually right here there is a current IX flowing right through there. And before we had these two branches. This branch was here to the side, and this branch was right here diagonal as well, and they were both connected at one node, and that one node was connected to the wire. And if you use the definition of what a node is, then you could redraw your circuit to look exactly like this, because a node is just two or more things interconnected. And so notice how we have no components between these wires. So this whole wire is acting as one node. So you can go ahead and break and split that up or join however you want to solve the problem. And also, if you notice this bottom piece right here, there's nothing connected between these nodes. So you can also join and separate nodes at will. So that's just one portion of this problem that you should be able to understand, is the definition of what a node is. So yeah, let's go ahead and continue to solve this problem. Okay, so the way I was taught nodal analysis is in very few easy steps, and here I have them listed out. So step one is to obviously identify your essential nodes. In fact, you should be just identify all your nodes, but your essential ones are definitely what you're going to need to break down this equation. Break down the circuit. So, and then step two, you have to identify your reference node. And well, let me just go ahead and erase that S because it's just one node. You just have one reference node that you're going to identify. And then step three is to write KCL equations going outward from your essential node to your reference node. So all this should go straight down to your reference node from whatever direction or whatever branch. And you can also go and write your KCL equations of all the currents going into the reference node. But I like to do it like this. So check this out. All right, so here I've identified my reference node. And just to make this clear, I wrote down my reference at each point down here, because just to illustrate that all of this is one node. And here's another essential node that I identified. I'm going to call that V1. And just to show you that all these points, and even that point right there, is all one node. So that's V1. And then here is also another node. It's not essential, but it's a node. And we'll definitely use this. And I'm going to label that V2. So now that I have everything identified, I'm going to go ahead and start writing my KCL equations. And if you don't know what KCL is, then I suggest that you go and you do some reading, because in this video I'm not going to explain what KCL is. I'll explain how I formulated the equations, but I'm not going to explain anything behind the KCL methods or anything like that. Alright, so I'm going to start from drawing my nodes, my KCLs from left to right on this circuit. And again, we start from our node. This is technically one node, but we'll start from right here. And we'll do all the currents coming outward of this node. So, And we all know that I is equal to V over R, you know? So this is what we're going to use to develop our KCL equations. So our first equation, or our first term in our node here, we just have this one node, is going to be the voltage at this potential minus the voltage at this potential divided by the resistance in this branch. And the resistance in this branch is only 6 ohms. So here we go. So we have V1 minus V2 is equal, or divided by 6. And then we're going to have a plus there. And in this next branch, we're going to have the voltage here divided by the resistance in this branch. But remember that we're writing KCL equations. So, and technically the correct way to write this equation is the voltage here minus the voltage here divided by the resistance in this branch. And that's going to be V1 minus, we have a ground here, so that's going to be minus 0 divided by 12 ohms. And now here in this next branch, we already know the current in this branch. It's sitting right there in front of us, but it's going against where we're measuring, where I'm measuring. It's going against it. So that is going to be negative 2 amps. Negative 2 amps. And now in the next branch, we're going to do the potential. Well, actually, hold on. I actually forgot something very important and very crucial into this equation, and I'm going to go ahead and add it. So, important thing that I forgot to add was in the original circuit, we had a voltage that was mentioned in this branch, and it was given to us, and that voltage was 8 volts. So I'm sorry if you got a little confused there, but we have a voltage in that branch, and it is 8 volts. So since we know the voltage in that branch, and we also know the resistance in that branch, V divided by R is going to give us the current. So we don't need to do this extra equation. We can go ahead and just write the current. So 8 divided by 4 is going to be 2. So that's going to be our next current in our equation. So now we just have this current, which is flowing in the same direction as how I'm measuring here from V1. So that's just going to be a plus 3ix coming from that dependent current source. All right, so now, and all this is going to be equal to 0, correct? Because all of the currents leaving the node or entering the node, all the currents leaving the node should be equal to 0. All the currents entering the node should be equal to 0, right? So that is our first equation, and notice how we have 3 unknowns. We have V1, V2, and we have Ix as an unknown. So now we're going to have to look back up at our circuit and figure out how can we solve for Ix, essentially, because V1 and V2 are the 2 unknowns that we can handle, you know what I'm saying? We can handle 2 unknowns. But now we have to figure out what Ix is. So if you notice here, Ix is flowing into this node right here. And if you also notice, 3Ix is flowing directly into here as well. And if you also pay attention to the passive sign convention, we're going to have a current from this greater potential flowing down to this lesser potential here. So whatever that current is, it's flowing down there. And we already know what the current is. The current is 2 amps in that branch. So since we have 3 currents flowing into this one node, then we should be able to write an equation to solve for Ix, and I'm gonna go ahead and show you it right now. All right, so right here is our equation that we've created from this smaller KCL in our circuit. This is a smaller KCL in our circuit, and we had to do this so that we can create an equation so that now we can now solve for Ix. And if you don't understand what's going on, this current Ix is flowing into this node. This current 3Ix is flowing from here into this node, and this 2 is flowing down through this resistor into this node. So all of these currents added up should equal to 0. So now let's go ahead and solve for that. It's just a little bit of algebra. So yeah. All right, so after you solve that, you should get something exactly like this. So just a little bit of algebra, and we'll eventually get that Ix is equal to -1/2. And this is going to be crucial to solving our circuit because we need this in our equation right here. So, yep. Go ahead and just understand how we did this and how we got Ix is equal to -1/2. All right, now that we know what Ix is, we can now safely break down this equation, you know what I'm saying, reduce this equation and solve a little bit. So I'm gonna go ahead and do that. And yeah, it's just a little bit of algebra, nothing too crazy. And yeah, so check this out. All right, so this is how I have reduced the equation, and it's just some algebra, you know. So this should be something that you should be comfortable with. So I'm not going to go into details on what I did in the algebra. So I've come to this equation here. So I have V1 and V2 as my unknowns, and all of this is equal to 0, right? So if we look back at our circuit, and we take some time to really think about what's going on with this node up here, right? What's going on up there, you know? We don't know what it is, but how can we figure out what it is? And it's quite simple. If you remember the principles of voltage across parallel branches, then you would know that voltage across parallel branches are all equal. Adjacent parallel branches are all equal, right? Something like that. So, we know the voltage going across this branch right here. We know we have 8 ohms right here at the top of this branch. So we should also have an 8 ohms at this point and at this point if the principle still holds. So we should have V1 should be equal to 8 volts as well. And I'll go ahead and illustrate that right here. So V1 should also be equal to 8 volts. And that's good. So now we only have one unknown in our equation, right? So we can go ahead and just plug that in. So I'm going to go ahead and do that. All right, so here is the rest of the algebra and broken down into a couple of simple steps. Here we plugged in our 8 volts for V1, and we just went ahead and solved it, you know, simple algebra, just went ahead and solved it, and we ended up getting V2 is equal to 3. So now, what do we know about that? So V2 isn't exactly Vs, but what do we know about that? Let's go back up to our circuit. So we know that V2 is this node sitting right here, right? And so this node right here is carrying the potential that's sitting right here on this battery. So technically, and quite literally, V2 is equal to Vs. So we have solved our problem. Vs is 3 volts. I hope you guys understand that. and take back what was used to solve that. We used some KCL. We used another little KCL here. We had to understand the concept of what a node is, and we also had to understand our passive sign convention as well. So I hope you guys take a little something back from this circuit, because we're going to need it, the concepts that were used in this circuit, to carry on in the course. Thank you.